Okay, with that, let's go ahead and get started with the webinar. As I said before, my name is Damon Tordini. I'm a simulation application specialist here at Hawkridge Systems, and I tend to focus on all the simulation tools, but particularly flow simulation. And so what we're going to be talking about today is the usefulness of this product, what the typical applications it's going to be used for, and how it can sort of improve the design process, specifically related to high-tech electronics. We're talking about pretty much any kind of power electronics that will go in some sort of enclosure, most likely. So obviously we could mean anything from computers, networking equipment, servers, specialized control boxes, basically anything. And of course, that's a pretty common use for SOLIDWORKS, designing all those components, especially if you're using things like CircuitWorks to bring in a circuit board design and generate a 3D model off of it. So let me start by asking everyone a question to think about very quickly. If you are examining a product, maybe you're just in the conceptual design phase, maybe you've proceeded a little further beyond that. If you're designing anything related to electronics, the first question that probably pops into your mind is this thing too hot? Is this thing going to operate under acceptable temperatures? And of course, if anyone is related to that industry or has familiarity with it, you're probably going to be aware of the fact that most of the time that's the challenge in a new product, specifically because most new products tend to follow these industry trends that we've seen the last several years of getting smaller, more compacted enclosures, more powerful, obviously more processing power, or more powerful radios or whatever kind of equipment we're referring to. And so it gets harder and harder to keep these things operating cool, keep them operating within acceptable temperature. And of course, it's not always realistic to just build a new chip, for example. Most likely wouldn't be a chip, but build a new heatsink, maybe build a new enclosure, whatever it may be, just to test the thermal characteristics of it. So we need another solution to figure out what design is going to work in all these cases, whether it's heatsink or anything else. Maybe it's just the board layout. And so obviously, if we could simulate the operating conditions of that new product, it would be beneficial. So a solution for us is going to be to use CFD software to do that. And ideally, if we have a CFD tool that is easy to use and something that we can use to sort of predict the performance very quickly while we're still in the early design phase and not have to wait until we have a finalized model, then that's something that obviously is going to help you make better decisions as you go along. So if we were referring to CFD software in the realm of SOLIDWORKS simulation products, we're talking about SOLIDWORKS Flow Simulation. So SOLIDWORKS Flow Simulation, that is our built-in CFD tool, Computational Fluid Dynamics, and that is essentially a general-purpose fluid flow and heat transfer simulation tool integrated directly into SOLIDWORKS, as we mentioned. So it is essentially designed to allow you to take any 3D model, whether it's a SOLIDWORKS model or something you imported into SOLIDWORKS, and quickly run CFD analysis on that to figure out not only what any kind of fluid flow is doing, velocities, pressures, recirculation, anything like that, but also any of the heat transfer effects associated with it. And the general idea behind flow simulation is to make a CFD tool as easy to use as possible in the design environment that you're already working in SOLIDWORKS, so that you don't have to rely on a dedicated analyst to evaluate a design that you've come up with after the fact or after it's too late. And in fact, by using a CFD tool that's built into your modeling program like SOLIDWORKS, you can kind of break down that barrier and get a lot more value out of whatever information it is you obtain from a simulation, from a CFD tool. Now, some of you may be aware that we also have a thermal study that's part of SOLIDWORKS Simulation Professional. If I go back here, SOLIDWORKS Simulation Professional is just one of our SOLIDWORKS simulation tools, part of the FEA family of products. And so sometimes there is a question that arises, why would you use flow simulation for a thermal problem when there's also this thermal study in the SOLIDWORKS simulation tools? And the answer to that is that the thermal study in SOLIDWORKS Simulation Professional is still what we call an FEA, finite element analysis study, which means that it only analyzes the solid geometry. So if I had this heatsink, for example, with a chip on it, there's some heat source. The main method of cooling that heatsink is the airflow around it. But the thermal study in SimPro wouldn't be able to do that. It would essentially require us to put in a number called the conduction coefficient, which is basically a prediction or a very rough approximation of what the airflow would be doing and how much heat it would be able to pull away from the model. So one of the big unknowns in the simulation you unfortunately have to enter yourself in that thermal study. So it's not always a good idea to use that if airflow is the main thing that's keeping your product cool. And so that's where flow simulation comes in. Flow simulation, being a CFD tool, calculates all of those flow properties for you, velocities and flow rates and whatnot. So you don't have to make any of those assumptions. And the design of the heatsink, for example, how many fins there are or how big they are, and how much surface area there is going to be directly shown to you by the calculation of what the air is doing. Especially if you were to change things like orientation. If we flip that heatsink on its side, we know that the air is not going to move as cleanly through the fins as you're seeing in that image. And so the CFD tool will be able to show us that, whereas the thermal study wouldn't. So if you're going to use SOLIDWORKS Flow Simulation, here's the general process or procedure that we'll go through. You'd have your SOLIDWORKS geometry, something you modeled in SOLIDWORKS most likely. And then what we're going to use is this thing called the project wizard, which will basically help us set up all of the main concerns about the simulation. What kind of fluid it is, what's sort of the domain of the problem, where do we want to analyze the fluid, and what kinds of conditions are important. And then we'll establish all of our flow conditions, our inlets and outlets, our heat sources, where is the heat being generated, like on chips, for example, or any other devices, transformers or whatnot, capacitors. We'll apply any other material conditions that might be necessary. And then once we have all that set up, we'll run the analysis and review the results, of course. And then if we don't like what we see or we see some room for improvement, we'll change the model, most likely, or we could even change materials or other things. And then we'll just run the analysis again, and being an integrated CFD tool, then we'll get those results right away without having to re-export the model or redo any of the setup work. And we'll even be able to automate that process a little bit if necessary, where we could sort of examine a large batch of design options all at once, or even run an optimization mode where we could sort of look for the best value of something, like the best value of a wall thickness dimension, or a thickness of a heatsink fin, or how many fins you have, or even dimensions to locate different components throughout the model. So what we're going to look at here as a case study is this compact CPU enclosure. Again, kind of following the trend of plugging more powerful hardware into a smaller space. So we've got this little tiny bank of 3 40mm fans. So if you know anything about typical computers, those are real small fans, and most likely in a regular traditional scenario, they wouldn't do much as far as cooling it. But if we kind of get creative and design a neat enclosure that has 3 of them right there, kind of pumping air right through the whole case, right out the other side, might be enough to keep it under that constraint we have of 68 degrees. So we're going to do things like analyze our sort of baseline design that we think will work, and then we'll take a look and try to compare all these different design options we have. And we'll look at some results that have been compiled after we have run all those types of analyses, figure out which design is going to work the best. And mainly what we're looking at here is the packaging design, whether we want vents in the housing somewhere, or if we need grills on the fan or things like that. And how many fans do we actually need? Do we need all 3 of those fans there, or can we get away with 1 or 2? So the general procedure, again, it's going to look something like this. I'm going to launch SOLIDWORKS 2015, of course. And we'll go ahead and open up our model that we've got here. So this is the electronics assembly. Again, it's got the PCBs modeled in there with most of the components that are important. We've got the main chip, the main CPU there with the heatsink on it. And we've got some auxiliary PCBs with the RAM chips over on the right side. And basically, as you can see right here, the initial design was to have vents at each end of the case. and then 3 fans sort of located on the circuit board. So we'll examine if that is the best position or not to put those fans, and see if there's an improvement that can be made. First of all, I just want to also point out that this is a little bit of a simplified version of the model. The original one probably has more detail in the case. For example, we've got some cutouts, or in the top of the enclosure we've got some slit vents, and then also we have sort of a perforated hole pattern over the fans. And as you'll see, we can get rid of that detail for now because we're going to have another way to approximate those small holes or small slits in the case without actually having to include them in the model. We have what's called a perforated plate functionality in Flow Simulation, which will speed up the analysis and still let us take that into account. So the first thing we would want to do in most of these situations is decide if we want to do an internal or external analysis. Flow Simulation is capable of either, meaning we could analyze the airflow inside the box, or we could analyze the airflow around the outside of the box and around the enclosure, and even underneath it if it was sitting on a table, for example. And we could even do both at the same time. And so the question would be, what's important for the analysis? And in this case, since we're talking about fans that are going to be sucking air in through those small inlets, the airflow around the box probably isn't that important. The internal airflow is really the key here. So it's probably a safe bet to only focus on the internal airflow and not worry too much about the currents in the room, for example, or wherever this thing is going to be mounted. So that being the case, the first thing you'll usually want to do is to just verify that your model is properly sealed off so that the internal space, the empty space where the air would be, can be recognized by Flow Simulation. If I do a quick section view, you'll be able to see in this model that basically the inlets that I have been filled in. So the fan vents on the opposite side and the inlet vents over here have essentially just an extrusion filled in there, which we call a lid. And so that allows the program to figure out where to do the calculations, where that fluid region is. And it also gives us a location to put in our boundary conditions. We have to define if those are inlets or outlets or what the air is going to be allowed to do at those spots. So we need a face to click on to do that. And so that's why we cap these things off. And if you've done it properly, you should be a quick check of the geometry, which we can turn on right here. We'll just go ahead and hit check. It's going to calculate the fluid and solid volumes for us, which we'll then be able to see on the screen. And as long as everything looks blue as far as where you'd expect the fluid to be, you know you did it right. We also have some pretty cool leak tracking tools. If, for whatever reason, you can't figure out how to close off your model, or if you've got a gap somewhere that you can't find, it'll help you locate it. So let's go ahead and start a new project now, which will allow us to set up all the conditions we need. And I'm going to use the wizard. Most of the time that's the preferred way of doing things. It's a little bit faster. And so I'll just give this a new name. Let's call this Baseline Design B. And of course I can pick any configuration in the model that I want to use, so that later if I've run this project, I can then run it again for other configurations and compare different designs side by side. It's a very useful way of taking advantage of configurations and that capability that exists in SOLIDWORKS to see if you're making things better or worse when you make design changes. So first of all, we just have to pick some unit systems very quickly. You can pick all the standard ones, of course, or you can also modify them. You can save it as your own standard if necessary. So for example, I might want to keep SI units but use Celsius for temperature, and then I can just save that as the Damon system, which would be really cool. I wish I had my own unit system. Alright, so the next screen here is analysis type, and this is that screen where we set most of the physical feature conditions to basically to tell the software the scope of the analysis, what physical conditions or processes are actually important. So we already decided that it should be an internal analysis, so we'll leave that as is. If we look down the list here, we can see some things that we definitely do want, like heat conduction in solids. We need to turn that on if we want to see any of the temperatures in those solid parts, otherwise they wouldn't be calculated. And if gravity was important, we would also turn that on. would probably be more important if this was a natural convection problem where we were trying to rely only on heat sinks without any fans. So we would turn that on in this case, or in that case, and make sure that the direction of gravity is correct for whatever the orientation of this thing's supposed to be. I'm going to leave it off here, though, because with those fans, the orientation most likely is not going to be a key contributor. So gravity is not really going to affect things too much with those fans. And then also, just so you're aware of it, we could account for radiation as well, which might be important if this thing was outside, maybe in the sun, and the casing was going to be heated up just by the sunlight hitting it. Or if it was a space-based application, radiation would definitely be important. Also, we could do rotation, which refers to the ability to actually spin some of the solid geometry in the model. That's usually used for pumps or things like impellers or fans or any other blower. Most of the time, you're probably not going to use it in the electronics cooling industry here because any fans that you're using will most likely already be designed and not something new that you are creating, in which case you would have the data of the fan curve that you could put in. If, however, you were trying to design a new fan or CPU cooler, that rotation capability would be able to do that for you. You'd be able to spin up the actual blades of the fan and see things like the volume flow rate at certain RPMs and the pressure across the fan, and that would help you design such products. Anything related to cooling will be pretty beneficial there. And then finally, these studies by default will be what we call a steady state analysis, which basically is going to show us the results if we left all of these conditions running for a very long period of time. But we could do it as a time-dependent analysis instead, which would just show us what happens when we run the study for a certain amount of real-world time, like 5 minutes. And we could see things heating up, or how long it takes for the system to cool down after we shut it off, or thermal cycling, or anything like that. As far as the fluids go, we have a pretty wide assortment of fluids in flow simulation, but if you're talking about electronics cooling, most of the time we will most likely be picking air. Most products are air-cooled. If you do have water cooling, of course, water is available as well in the liquids category. And we do have the ability to add multiple fluids, and so you would be able to do, for example, a simulation of a water cooling system where the water is inside a closed loop, like a water cooling pump connected to all the lines in the water block, and then the air would be simulated around the outside of that, so that you get sort of that conjugate heat transfer and be able to see the effect of the radiator and things like that. In this case, we don't have any water cooling, so we'll stick with just air. We also now need to pick our default solid material. The solid materials are important, of course, for properties like thermal conductivity. We want to know how hot they're going to get. So we need to pick a default solid, and then we can also apply the other materials later. And so usually for this menu, you'll just pick the most common solid material. So for example, I can just pick aluminum here. And you may notice that this is a separate materials database in Flow Simulation. It's not the same as the one in SOLIDWORKS, and there is a reason for that. Most of the properties that you'll need for these types of studies, such as thermal conductivity and specific heat, they have temperature-dependent properties, and so the Flow Simulation Engineering database has much more of that data than the basic SOLIDWORKS library does. Okay, getting to the end here, we can pick some wall conditions if necessary. So, for example, by default, we would assume adiabatic wall, which means that the walls will be perfect insulators, more or less. But if we wanted to account for some heat loss to the room, we could put in any of these other heat transfer coefficients or heat generation rates, which would allow us to mimic that. Also, by default, all surfaces will be treated as perfectly smooth, but we can add some roughness to them if we think that will make a difference as far as the boundary layer formation or flow rates or velocities. We can also set our initial conditions, which are, of course, important to make sure that this is going to be simulated in the right environment, right? Maybe it's operating in a nice, cozy room at sea level in a lab somewhere, or it could be, in the high desert, or it could be in Antarctica, or you never know. So you would be able to change those pressures and temperatures for a more realistic scenario, of course. Finally, the last thing here is where we set what's called the result resolution. And this is one of the key technologies of flow simulation, which is that the mesher is powerful enough such that you don't need much manual control, no matter what your geometry looks like. Essentially, we can pick one of the options on this result resolution slider. Higher it means more refinement, but it also means higher solve time. And more or less, the mesh will just work in basically every case. You can of course, manually tweak the mesh if you want to. You'll see you can plug in things like the gap size or wall thickness that you want to make sure the mesh captures. But more or less, you can leave it at sort of the mid-range values of there, 3, 4, or 5, and you'll get some decent results in most cases. If you want to push it to higher levels, like 6 and above, that's useful for things like academic studies, where you're really trying to get the best accuracy possible out of the software and not have any mesh error. And we can even turn on some neat technologies such as the solution adaptive mesh, which will essentially look at the results of your simulation, and if it sees any discrepancies, it sees any big variance in the results in any area, it'll refine the mesh there as well, just right in the empty space where the gas is. So we'll leave this at a 3 and hit finish. And now we have our new project with that wireframe box you see there in the graphics area. That's our computational domain. That's basically just the box encompassing the model and where all the fluid's going to be. So at this point, most of the work is done, and the only thing that's left is to apply those boundary conditions and the materials and heat sources and things like that, which usually will be necessary for any of these electronics cooling problems. So first of all, for boundary conditions, these again define whether any of the openings in your model are an inlet or an outlet, or perhaps some other kind of opening and you don't know which one is which. So if I do a section view again, it'll make it a little easier to see inside the box here and pick these faces. And what I could do is go pick my boundary condition and select, for example, these 3 faces at the inlet here. And if I knew that they were inlets and had a certain flow rate associated with them, I could define a volume flow rate. I could put in a certain number of CFM, for example. In this case, however, I've got those fans mounted inside the box already, and that's the only thing that's going to be blowing the air around. These are just supposed to be vents that are basically open to the air. So if that's the case, and they're not an inlet or an outlet with a specific flow rate, I can instead define them as what's called a pressure opening, where all I have to do is select what the pressure is on the other side of that face, essentially what the pressure in the room would be. And you can see that down below there in the box, it's already got the correct temperature and pressure filled in from the from the environmental conditions that I picked earlier. So these 3 faces should just be these pressure openings exposed to the room, same as the other ones on the opposite end of the case. So I'm going to have 6 faces total that are pressure openings. And as it turns out, I've also got 4 more that are going to be in the top and bottom of the case. But I'll go ahead and skip that for right now. So then the question becomes, if I'm not defining the flow rate at the boundary conditions, in the boundary conditions at those inlets or outlets, how do I define that? How do I set up these fans? Well, we could put flow rates on the faces of the fans too, but that wouldn't be very realistic, especially because in this case they are supposed to be recirculating the air that's in the box. The other aspect that's unique about fans is that they put out varying amounts of air depending on the pressures on each side of the fan. So in order to account for that, flow simulation has the ability to define a fan curve, which basically will let us pick the faces where the air will be coming out and then select a predefined fan profile that has all of that data in there, flow rate versus pressure. So I'm going to define some internal fans here. Let's go ahead and just pick this one and this face here for where it enters the fan. So basically the air is going to be cycled through these faces here, and if we scroll down, we can pick from the library of which fan curve we want to use. We get a few choices in the default flow simulation database here, mostly from the manufacturer Pabst. Not that Pabst, if you're thinking. But we've got some Series 400 fans here. Here's a Series 405 F. And if you look at these fan definitions, we can go into the engineering database and take a look at the properties. We have a table of pressure drop versus volume flow rate. And it even shows that stall region that's pretty realistic in most fan or pump applications. So we'll be able to see if we put the fans in a bad place and the flow rate is being restricted a lot because of pressure buildup. So it'll be much more accurate than just assuming a certain CFM, which would basically mean that we're assuming the fan will operate, as fast as we need it to, when that may not be the case. So there's my first fan, and of course I would go and define the other three as well there to finish that up. The next thing we need to do is put in the other materials that we hadn't specified yet. Remember, the default we picked was aluminum, so we would need to pick anything that's not aluminum and define that in the model. So for example, these capacitors here I could select, and if those are supposed to be silicon, I could go to my semiconductors category and pick silicon. Also, of course, we've got our chip there, our main CPU. So that also will be a material that we would assign to it. We probably wouldn't assign silicon. It'd be more realistic in most cases to do something like a ceramic, because you're also accounting for the housing or the substrate that the chip is printed on. So pure silicon is not usually a great approximation for those parts. So we can pick some ceramic material like an alumina, which would be a little more realistic. Although there's also another way you could set up the heat transfer properties for these chips, which I'll talk about at the end of the presentation. For right now, we're just going to put a material on them like I just did, and then also we'll be putting on a heat source. So the materials would all be set up. Maybe the last one that I'll do here is the circuit board. We could pick the PCB there, and as you may be aware, circuit boards are made up of layers of different materials, right? We've got your substrate basically for the board, and then the trace material, which is usually something like copper. So to account for that, and account for the fact that there's different properties in the different directions of the board, we do have some non-isotropic materials in here, such as a 4-layer or 8-layer PCB, and that'll account for the fact that the board conducts very poorly through the thickness of the board, but it conducts heat much better down the in the plane of the board, down the length or width of it. And so we just need to make sure we set the direction of that anisotropy properly. So now it knows through the thickness of the board, it doesn't conduct as well. Okay. Getting close to the end here, the last thing we would need to do as far as the heat transfer is set up our sources. We can define either surface or volume sources, which basically means that heat is going to be generated by some process on that surface that we pick or throughout the volume that we select. It doesn't really matter the real world conditions that are causing that heat to be generated. We're just telling the software to sort of create some heat in a certain location. So for example, I could pick the CPU there and just type in whatever the heat power is, whatever wattage that is, that I want to assume is being generated, something like 20 watts, for example. And usually most chips will have a thermal design power that you could look up and choose that number from. And maybe we would set the other components, like these chips on the RAM sticks, to have their own wattages, or we could even do things like define a known heat generation rate, which is basically just wattage per area. So it's similar but a different unit. Okay. So again, all of our heat sources would be generated, and so at that point the heat would sort of be created in those areas that we selected. It would conduct through all the solid components, which by default will have a perfect conduction between them, and then of course the conduction will be based on the material that we select and the thermal conductivity. And then the air, of course, will carry that heat away through convection and basically through the fans and out the enclosure, and that will determine all the temperatures in this design. Now, if we want to get a detailed reading of the temperatures in certain areas, aside from all the visual plots we're going to be able to look at, we have these goals that we can define as well. And so goals are basically like sensors to help you track the key results that you're worried about. So for example, I might just want to know what's the average temperature in this box, so I could define what we call a global goal to find that. You could just say average temperature fluid, global goal. And maybe I also want to know what the maximum CPU temperature is. So I could define what's called a volume goal, select that component, and then again find temperature. This time it would be the solid temperature, and check the max column. So that'll tell me what is the highest temperature anywhere in that part. Makes it much easier to see if any of your design requirements are being violated in a particular version of your product. So at this point, we would mesh and then run the simulation. I'll just go ahead and generate the mesh here so we can see what that looks like. The solver window is going to come up. It's basically going to generate a Cartesian-style grid, an XYZ type grid, and then start subdividing that grid, splitting it up, and refining what we call the cells of the mesh to match the solid geometry better and make it more accurate. So this mesh most likely is going to be somewhere around 100,000 cells or so, maybe a little more. And just for comparison, I'm using an HP laptop right now. I am on, this is about a 1.5 to 2-year-old HP laptop with a Core i7 processor and 8 gigs of RAM. And so with that sort of much RAM, those system specs, I typically could solve a problem into the 4 to 5 million cell range, most likely, without having too many memory issues. Whereas here, I'm going to only be in about the 150,000 cell range, so nowhere near the limits of what you would be able to do as far as detail in the geometry. And that's usually important for these electronics cooling applications because there is so much more detail that you have to worry about with all the different chips and components on your PCBs and the complex housing that it might be in. There might be a lot of narrow channels in different areas. So the mesh has been generated, which we could look at here in a nice little preview. If we sweep back and forth, as you can see, it's basically an XYZ grid that's been subdivided, and we have this unique, what we call partial cell technology, to account for the correct shape of the geometry, even in areas like this where it's a little curved or it's not matching up to the boundary of the cell properly. We will actually be able to detect where that solid surface is within the cell and split the cell up there properly so that the boundary layer is calculated the right way. So let's go ahead and switch over to the version of this that I had run before with all the materials and the fan set up properly, as well as the heat sources. You'll also notice there's some extra things in here that I've defined, such as this perforated plate creation. The perforated plate definition that I created is the thing that's going to allow us to mimic the behavior of those small holes, those small perforations that were actually in the case that I didn't include in the model here. So the perforated plate lets you plug in what the dimensions of those holes are, and it calculates what we call a free area ratio, which basically tells the software how much air is actually getting through those holes, rather than assuming they're completely open. So this is telling us, for example, that those perforations are really only making about 46% of that opening open to the air. The rest of it is filled in by the solid. So we've got those defined at the inlets and outlets, and also these vertical vents or slots in the top and bottom of the housing. So typically the first thing you'll do when you run a simulation like this is go straight to the goals and check out whether or not you're violating any of your design constraints. So let's go to our goal plots, and the first thing we have here is one that I created called main chip. And this is just showing me the max temperature of that CPU like I showed you. Plus, it's showing me some information about the volume flow rate through the inlets here. So if I click Show, it looks like right now my max temperature of the CPU is about 59 degrees Celsius. So we are within our design spec of 68 degrees with the baseline design here. So that's obviously a good thing. We can also see that the case temperature on average is about, or excuse me, the maximum case temperature is about 87 to 88 degrees. And then I've got about 9 cubic meters per hour flow rate, which of course you could convert to CFM if you wanted to. So the question becomes, is this the best version of the design, or can we make things better and how can we make things better. And usually, if you're going to be changing the design, the best way to decide how to do that is to look at these visual plots, such as cut plots, which can take a slice through the 3D model and show you any property you want, from velocity to pressure, turbulence properties, vorticity, basically anything. And we can actually sweep those through the model up and down. So it makes it very easy to see, for example, right now, that with the fans placed the way they are, most of the air is being pushed right to the immediate vicinity of the PCB and somewhat through the heat sink that's placed in front of it, but it's kind of petering out towards the end. There's not much velocity as we get near the outlets. We could also view these on any other plane, of course, and this one I've got showing what we call the streamlines as well, overlaid onto the cut plot, which makes it easier to see sort of the direction of the airflow and whether or not you've got any recirculation happening, which we in fact do in some of these locations here. Looks like this isn't particularly vented well or directed well as far as the airflow. So some of the air is getting past the CPU, but maybe it could be improved. Maybe these other fans that we have at the other side of the circuit board that aren't blowing air right on the CPU are not as important. That's something that we could look at. Of course, we have a lot of other ways to visualize all these results, and the most popular way to do that is with the flow trajectories. This is basically a three-dimensional view of where the air or any other fluid is doing, and again, we can show things like temperature on here, which in this case is allowing us to see that the air is nice and cold when it comes out of the fans, but the way that we position the fans, a lot of the air is just kind of recirculating under the housing or under the circuit board in the housing, where it's heating up a bit, maybe like 15 or even 20 degrees, and then it's just going right back into the fan, which obviously is not going to be great if we're trying to pump cool air onto that CPU. So maybe the fan placement is not ideal. That's what we could determine perhaps from these plots. So of course at that point we would want to make a design change, change any of the dimensions, any of the parts of the model, change the fan design if we even wanted to, if we were involved in that. And of course, once you change the design, you could either just hit run again, or if you had chosen to make another configuration, like I've done here, then I could copy my project to that new configuration and run that so I have something to compare to side by side. So for example, in this version of the model, I've now moved the fans so that they're actually on the housing. They're actually mounted here to the exterior rather than being on the circuit board inside. And so the only thing I would have had to change in my definition here is having my fans set up at those inlets rather than the boundary conditions that I had before, rather than the pressure openings. Everything else would be the same setup. I wouldn't have had to modify the heat sources or any of that. The mesh would be regenerated automatically, and then of course I would run and I would get my results. And just for a sort of a comparison, if you're curious, this one would run in a little over 10 minutes. 10 to 15 minutes is pretty normal for mesh of this size. So we could look at our cut plots and our flow trajectories now, for example, and see that we've been able to eliminate a lot of that recirculation and get rid of that warm air passing back underneath the circuit board just to get pumped through again. And of course, if we want to know if it actually made a difference, we can go check out our goals plot, and we can even use a neat tool we have called the compare tool, which is very useful, particularly in these electronics cases, where you can look at two versions of your model side by side. Let's look at the external fans and then the original internal fans one, and compare those goal plots that we have. And we can see that, for example, the max temperature of the air in the case has dropped. It was 87 or 88 degrees Celsius, and now it's about 78. And the maximum CPU temperature dropped too. It was about 60 or 59, and we've dropped it down to 46 just by moving the fans. So obviously, even though we were meeting our requirement before, we've been able to test very quick change, just moving the fans to the outside of the case, and verify that it made a huge difference in the cooling effectiveness of those fans, such that we might not even need all three of them anymore. And of course, we could continue down this road of trying new versions of the design, running the simulation again, and comparing to see which one is better or if we've made things worse. So along that theme, if we were to do so and try to answer some of these questions like, do we need those vents in the top of the case? Or where should the fans be? How many fans do we need? Compiling all those results can give us some pretty powerful information for this design and future designs. So we can start to do things like compare the cut plots between having vents or not having vents. It looks like in this case, for example, if we're looking at these 3 different temperatures, the maximum CPU temperature on the left there, and the RAM temperatures on the right, for example, looks like in most cases, removing the vent does make the temperature go up. So in this case, we do want to keep those vents, it looks like. That's allowing more cool air in, which is usually a good thing. So we know we want the vents, but what about the fans? Now that we moved the fans to the outside, we saw that they're cooling the CPU much better than we actually need it to. Can we get rid of some of the fans, or do we need all 3? So we could do, again, these comparison studies, which would be as simple as basically turning off the fan boundary condition that I put in so that no air is going through that opening anymore. And I could run these in a batch using the parametric study capability, which would run all 6 at once with different flow rate numbers that I put in if I wanted to. And then I could get all these comparisons. A is 1 fan on the far left away from the CPU. B is 1 in the middle. C is 1 on the right, pointing right at the CPU. And of course, you have all these different configurations or combinations of those. And again, we'd be able to get some neat comparisons here, showing us that the one we definitely don't want is A, which is just a fan all the way on the left away from the CPU. But as it turns out, looks like C is pretty good. C is a fairly low CPU temperature and a low RAM temperature. The only one it's violating is the temperature of that IC package, which is sort of in the middle there. So again, we can figure out pretty quickly which of these scenarios is the best one, which one actually meets our requirements, and which one doesn't. So it looks like we should be able to get away with just 2 fans. For example, the orange one there is A and C, so just 1 fan on each end, or 1 fan on each side. So that's the general value of flow simulation for these electronics cooling applications. You can sort of take advantage of this technology to the next level by adding on something that's called the electronics cooling module, which may or may not be necessary depending on your application. But this extra electronics cooling module enables a few key technologies within flow simulation that you might want to either make the setup a little bit faster for these problems or to increase the accuracy a little bit. So let's just go through very quickly the sort of key points here. The first one is something called the PCB generator that you can get in this electronics cooling module. The idea here basically is that instead of having to create a material for your circuit board, which is what I showed earlier in the demo, this PCB generator would let us type in all the layer properties of the PCB, what those thicknesses are, and the coverage of the trace on the board, for example, how much area is covered, and then all the correct material properties will be calculated for you. So it's a little bit easier to get accurate information for how the circuit board is actually going to conduct that heat. A little bit easier than trying to do all that math on your own or create your own Excel spreadsheet. Probably the most important one in a lot of cases is what we call the 2-resistor model. 2-resistor model is a more accurate way of simulating typical chips like a processor or chipset for a motherboard. And basically what it does is it accounts for the fact that a chip is actually what we call case or heat spreader in most scenarios, plus the actual circuitry of the junction. So if you are receiving 2-resistor model data from your chip vendors, that would be the JC and JB values on a spec sheet. If you want to be able to enter those values directly into flow simulation to account for the heat transfer more accurately, that's what the electronics cooling module will let you do. So you won't have to put a material and a heat power onto your chip anymore. You'll just put those JC and JB values per the JDEC standard directly into the software, which should be more accurate in most cases. We can also account for heat pipes in the electronics cooling module. If you're using heat pipes in any of your products and you want to account for the heat being passed through from one end to the other, this is a very simplified way of representing the heat pipe. It doesn't actually try to compute the real boiling and condensing and stuff that's happening inside the heat pipe. It allows you to plug in what we call the effective thermal resistance, which is just a spec that you can usually get from the heat pipe manufacturer, whatever heat pipe you're using. And of course, that'll show you very quickly what the effect of the heat pipe is, how much heat gets passed around to the heat sink, for example, and if it's effective enough, or if you need a more powerful heat pipe. You can also do Joule heating in the electronics cooling module. This is important if you have any scenarios where the amount of heat generated in a circuit is not precisely known, and it's dependent on the electrical conditions that are happening in that component or in that circuit. So Joule heating allows you to define those electrical conditions, like the amperage and the voltage passing through a part. And then, of course, the resistance will be calculated, and then the resistance is documented in the material properties to have certain heat generation rate, depending on what the resistance is on that current. So a more accurate amount of heat generation can be calculated compared to just making an assumption and trying to type in a wattage value that you might not know. So any simulation of power buses or traces on a PCB or anything like that where there's a lot of current generated that's causing the heat, Joule heating is the key for that. And then finally, all of these typical items that you need to define in a flow simulation project, which come from the library, the engineering database, they will have additional options for you. It'll be an expanded library in this electronics cooling module. So we're talking about more materials, more fan curves, a lot more fan curves, more interface materials if we wanted to account for thermal pastes or pads or adhesives or whatever in between your chips and heat spreaders, for example. More thermoelectric coolers, and also a lot of 2 resistor component model definitions in that library. Okay, we're just about out of time. Before I finish, I just want to remind everybody of the upcoming Webinar Wednesday schedule. This morning was the high-tech electronics presentation for flow simulation. Coming up at 11, we have a SOLIDWORKS 2015 Greatest Hits Volume 3. If you haven't been able to see the rollout at this point of the new features in SOLIDWORKS 2015, Greatest Hits Volume 3 is dropping at 11 a.m. Make sure to catch that. Hopefully you'll find some hidden gems in there that you'll plug into your 8-track and be happy about. Next week on March 4th, we've got Intuitive Surface Design with SOLIDWORKS 2015. So focusing on some sort of organic modeling concepts. And then also at 11, we have our product education on SOLIDWORKS Composer, customizing the component library 101. So once again, I just want to thank everyone for attending today. If you have any questions about SOLIDWORKS Flow Simulation or any of the other simulation tools, feel free to email me, DamonT@HawkRidgeSYS.com. And of course, if you need any kind of Hawk Ridge Systems technical support, we're always available to you. Go to our website, support.hawkridgesys.com, or send an email to support@hawkridgesys.com. And of course, the phone information is on the website as well. So thanks again. We'll try to wrap up any questions if there are any left here. Otherwise, have a good rest of the day and enjoy the rest of your month.